Introduction scene. Hello and welcome. If you haven't seen any of my videos before, that's because there aren't any. So, let me introduce myself. I'm Will. I'm a PhD student at the University of Bristol, and I'm supervised by Dr. Ryan McConville. This talk is going to be a mimic of the presentation that I gave at Complex Networks 2023. So, let's dive right in. This talk is going to be on uncertainty in GNN Learning Evaluations, the importance of a consistent benchmark for community detection. So, what exactly is this task that we're going to be studying? Some of you may know, some of you may not, so I'll just give it a little brief introduction. Community detection with GNNs is the task of classifying a graph into communities of nodes. So, how exactly do we do this? Well, we're going to be doing it with GNNs. What GNNs are, if you don't know, are a form of neural network that can process graph-structured information. We're going to be looking at attributed graphs, which means that they have a set of features as well as connectivity information. So, how exactly does a GNN process this? Well, each node has its features passed through a neural network, which are then aggregated along the connectivity information. This transfers the graph into the latent space, where clustering is more easy to perform because of our lower dimensionality. So, you don't really need to know the ins and outs of all these methods because we're looking at the evaluation of these methods. What you do need to know is that all of them have some hyperparameters that control trade-offs in the optimization, which can make the algorithms better or worse on certain tasks. So, now that we've explained the task that this paper sits in, what exactly is the problem? Well, essentially, we just don't know which one is best. These algorithms can be affected by two things: randomness and hyperparameters. So, how does randomness affect these methods? Well, when we split our data set, this calls up a random seed. When we initialize our networks, we use randomness. If we use Bayesian hyperparameter analysis, then we're drawing from probability distributions, which incurs randomness. If you're using contrastive learning, then you're also using randomness. So depending on which random seed you use, you can get very different results. The second thing is the hyperparameters. So typically the practice at the moment is to just say what the default hyperparameters are. But the thing is, the default hyperparameters don't work for every data set, and they're also specific to the random seed you're using. So if we look to our graph, then what I'm trying to illustrate here is that all of these different algorithms on this particular data set have very different results with the hyperparameters that we found through a hyperparameter optimization and the default hyperparameters given by the dashed lines. So the error bars is the variation due to a random seed, and as we can see, it's very clear that depending on the random seed you use, you get widely different performance rankings. So our problem just is that we don't know which algorithm is best because we're not carrying out a fair evaluation. Now the reason for this is because we have a publication bias where the incentive to publish good results means that you have to get good results, so you're slightly biased towards finding good results. This is an issue because it can affect real-world applications which depend on trustworthy results. So, now that you know the problem, what is the solution? Well, we're simply going to quantify how much randomness affects the different rankings of your algorithms. So, we're going to be adapting Kendall's W coefficient of concordance to measure the presence of randomness in our benchmarking procedure. So in our benchmarking, what you're going to be doing is you're going to be running your algorithms on different metrics and different data sets. Then you're going to be calculating this value and taking the average over all of those different data sets and metrics to see how your benchmarking procedure has been affected by randomness. The value that you're going to get out is going to be between 0 and 1. Where 1 means that your results are absolutely pointless and 0 means that they're absolutely perfect. and randomness hasn't affected them at all. So here is the maths and the code to show you how easy it is to implement for yourself, or you can pip install the package. So what is the solution to inconsistent evaluation practices? Well, it's simple. We just have to follow the same procedure for evaluation. To evaluate all of the methods in your benchmark fairly, all you need to do is carry out a hyperparameter optimization that is consistent across all of the different methods in your benchmark. To demonstrate why this is necessary, we're going to show you how much better your results can be if you carry out a hyperparameter optimization compared to just lifting the default values from each of the respective papers. Here is an overview of the investigation that we carry out, including the metrics, datasets, HPO resources and methods that we're going to be evaluating. All of these methods have been re-implemented and open sourced at the URL below. What we're going to do to compare these is rank all of the results under all of the different methods under hyperparameter optimization and with the default hyperparameters originally detailed. Now let's move on to the results. Here's an example test from our benchmarking investigation. This is the Cora dataset and the F1 scores. And what we're demonstrating here is that through the hyperparameter optimization, we've found more trustworthy and better results. So in the top graph, you can see the results ranking distribution is very spread out and overlaps between each of the different algorithms, whereas below, the algorithm ranking is more distinct. If we look at our framework comparison rank, which is which of the sets of hyperparameters has led to better results, where a lower value is better, we can see that the hyperparameter optimization has led to better results. Similarly, we can see that through our W randomness coefficient, the results are also more trustworthy, which is good. Move on to the results over the whole benchmarking investigation that compares the default hyperparameters and our hyperparameter optimization over all metrics and all datasets. What we can see here with our W randomness coefficient is that both sets of hyperparameters lead to equally trustworthy results. Now, this is probably because we've re-implemented all of these methods under the same framework. We've used model validation for all of the methods. We've carried out this investigation for the same number of epochs for all of the methods, and we've used the same random seeds for all of the different methods. However, if we look to our framework comparison rank, which tells us which set of hyperparameters led to better results, we can see that the hyperparameter optimization led to much better results overall. This means that our investigation got better algorithms. So, where's the take-home message here? Essentially, the hyperparameter optimization matters, and you must always carry out a consistent evaluation whenever you compare different machine learning algorithms. If we do this, we can not waste energy and time and GPU resources because we can actually lift results from other papers rather than simply lifting them and not carrying out a fair investigation, which leads to unfair model comparisons. Using our W randomness coefficient, we can quantify exactly how consistent our results are across random seeds, which leads to trust in the results, and from there, usability in real-world applications. This coefficient can be used for more tasks than just community detection. We can use it for any graph task you like, any large language model evaluation, or going back to the good old basics of sentiment analysis and object detection. That's the whole presentation. So hopefully you learned something, and thank you very much for listening. If you've got any questions, drop them in the comment section. If you want to find out more about me, then check out my website. But that's all I have time for today. So, peace out.